Hello everyone, my name is Jaya and I'm going to present the work Unmanned Aerial Vehicles as data collectors in the wireless sensor networks, investigation the effects of back and forth and spiral coverage paths in the network lifetime. Here I'd like to give you a brief outline of this presentation. Firstly, I'm going to talk about the introduction. So, wireless sensor network are distributed systems that consist of multiple nodes deployed in same area of interest to sense some phenomena that happened inside this area, as is illustrated in this figure. Normally, these nodes communicate with each other and with the sink through a multi-hop approach. And usually these sensor nodes are low-cost electronic devices with limited resources like, for example, limited communication radios, low memory, low computational capacity, and mainly a non-rechargeable battery. As I said before, the sensed events are sent to the sink by a multi-hop approach, and this approach discharges the battery of the nodes near the sink due to the overhooting of data. Another problem related of this kind of networks is the communication quality that can be compromised by noise, interference, and signal mitigation, for example. Now about the UAVs, lately unmanned aerial vehicles have been employed in several application domains involving terrain coverts, and that application is related to the problem with coverage path planning, that which consists of finding the routes that coverage every point of a certain area of interest, and these UAVs often perform coverage missions using geometric patterns like back and forth and spiral, for example. And these UAVs can also be used as data collectors in the wireless sensor network, and this can reduce the energy consumption of the nodes, avoiding message retransmission between with each other, and consequently prolonging the network lifetime. Recently, these UAVs as data collectors in WSN have been a target of many research, and each of these researches refer in terms of objectives like reducing the path size traveled by the UAV, for example, and increasing the time of flight, increasing the number of visited nodes during the flight. But as I said before, most studies have used metrics like path length or number of nodes collected without considering the network lifetime. Other ones address, for example, the UAV consumption optimization to maximize the flight coverage, but just only the work of Yang and Miao were evaluated strategies regarding the network lifetime, considering the impact of data collection in the sensor node's battery. However, no studies were found evaluating path planning algorithms to collect data from wireless sensor network. Well, say that the goal of this work is evaluate the use of UAVs as data collectors from the WSN, comparing the impact of back and forth and spiral path plannings in the battery discharge of the sensor nodes and of course consequently in the network lifetime. Now the methodology used. Both schemes, back and forth and spiral, were implemented in Eboracon Simulator, which is a simulation framework for model and simulation event triggered WSNs at a high level of abstraction. And for realize the comparison between back and forth and spiral and standard WSN with each other, was used metrics like number of captured events by the sync and the network lifetime measuring in days. Now the methodology used in the experiments. So our experiments were conducted in scenarios composed of a square measuring 810 square kilometers, and we investigated 4 scenarios of density, which 3 different relationships between communication and CPU loads in the nodes. Now for our experiments, the same configuration was executed 30 times, and the average results and the number of number of captured events and network lifetime was calculated, as the t-test was realized with 95% of confidence. Now I'm showing the experimental results of this work. This graph are showing the captured events for the configuration of 25% of communication per 75% of CPU loads, and it's important to mention before I show in the results that in our experiments performed, the UAV with path planning's algorithms overcomes the standard WSN approach that using the multi-hop approach. In this first scenario, for 39 nodes of density, spiral captured approximately 25 more events than BF and 69% more events than standard WSN, which 64 nodes of density spiral captured 12% more events than BF and 28% more events than standard wireless sensor network. For the density of H1 nodes, spiral captured just 1.4% more events than BF and 39% more events than standard WSN. And in the last scenario, spiral captured 6% more events than 5% more events than BF and 25% more events than standard WSN. Now about networking lifetime for this configuration. In relation to this, BF and spiral presents very equivalent results, as back and forth has spiral improves lifetime from 21 to 50 percent survived more days, depending to density tested, of course. And for the configuration for 50-50 between communication and CPU load, spiral captured 25% more events than BF and 138% more events than standard WSN. For the configuration of 64 nodes of density, Spyro captured 12% more days than BF and 60% more than standard table WSN. For H1 nodes, Spyro captured 1.7% more days than BF and 115% more events than standard table WSN. The last scenario, Spyro captured 5.9% more days than BF and 61.1% more days than standard table WSN. About the network lifetime for this configuration, again BF and Spyro presents very similar results for the lifetime in all densities. Using the UAV, you can improve lifetime from 60 until 140% more days than standard WSN. In the last configuration of communication and CPU, the scenario of 49 nodes of density, Spyro captured 25% more days than BF and 274% more days than standard WSN. With 64 nodes of density, Spyro captured 12% more events than BF and 116% more days than standard approach. With H1 nodes of density, Spyro captured 1.7 more events than back and forth, and 184% more events than standard table WSN. In the last scenario of density, Spyro captured 60.4% more days than BF and 86% more days than standard wireless sensor network. Now about the network lifetime for that configuration. Again, BF and Spyro presents very similar results, and we can observe using the UAV you can improve the network lifetime from 68 until 200% than standard WSN. Now, in our experiments, UAV with Spyro and back and forth overcomes the standard WSN. And it has been noticed that the more energy is spent on communication in the network, the more the UAV-based data overcomes the standard approach, both in relation to the number of sensed events and in the network lifetime. And when we compare the path planes with each other, in algorithms evaluated the number of captured events, the spiral path plane overcomes the back and forth approach. And in relation to network lifetime, both algorithms had similar results. Now finally the conclusions. In this work we have also analyzed the impact of using a UAV as data collector on the WSN, comparing the two most used flight partners, BF and Spyro, with each other and with the WSN. And we can it has been noticed that the larger communication cost is, more the UAV based data overcomes the standard WSN. And about the future reworks, we intend to explore other path planes algorithms and explore other WSN deployments like Randa 1 for example. And that's all folks, thank you very much.